these functions p, z, and d are the values of transition function for these arguments. Yeah, so these are the parts of the value of transition functions. Okay, so this is easy. So if we have delta, we can create such functions easily. We just have to look at the moves of m, so the values of delta, and define such functions. And now let's look at the computation of m. So assume that we are in some moment of the computation of m, and so we see that after, for example, t, like time, steps of computation. So we assume that t moves were executed, and after t steps of computation, of m, we have the following. Somewhere the head observes some cell on the tape, and we divide the tape into 3 parts. This part will be to the left of the head, the cell observed by the head, and the cells to the right of the head. To the left of the head, this is the first part. I will make a picture in a moment. The second part is the cell observed by the head, and the last one to the right of the head. Okay, so now I will try to make a picture. So this is the tape. So for example, here is the cell observed by the head. So this is head. A0, A1. I will denote the symbols here with A's, A, P. And this string will be called A of T, so to the left of the head. Here we know that here is some symbol ST, and the head, the control is in some state Q, and here will be this string to the right, P, for example, R, and this is B of T. Okay, so this is the situation on the tape after T moves, and after T moves, Q of T is the state of the control. So let with T of I denote the symbol in the ith cell of the table. Okay, so here we have this function. We have defined three functions: a of t, q of t, and b of t, and maybe s of t. So here is a of t, b of t. The state is q of t, and the cell, the symbol in the state in the cell observed by the head is s of t. So so before the computation, so for t equals 0, we have the following situation. The head observes the first cell, so a of 0 is empty, is 0. B of 0 is t1, t2, and so on, the input string without the initial symbol. S of 0 equals t of 0, so the beginning, the first symbol of the 0th symbol. And q is the initial state, so 1. Okay, so this is the situation before the computation, in moment t equals 0. Okay, so we assume that we have the values for some t, and how to compute the values for the after the next step. So maybe I will write the state of m and the content of the tape for t plus 1 can be computed in the following way. So we have to we are in some configuration, and we have to make one move. So assume that we have the values of these four functions for some moment t, and we will compute these values of this function for the next moment t plus 1. So let's see at a first, a t plus 1. So this depends on whether the head moves to the left or to the right. So we have to write these two cases here, and I will write it in this way. Maybe I will write it first, and then we will see that it is correct. Okay, so this looks complicated, but it is really not complicated, because so let's see here. If the head moves right, then d is 0. So here we have 1, and here we have 0. So this part corresponds to what's going on if the head moves right, and this part, and other case, if d is 1, then here we have 0, and here we have 1. So we have only this part. So this is a if the head moves to the right, and this is a t plus 1 if the head moves to the left. So if the head moves to the right, we have to append s of t to this string. So we multiply this string by 2. So we move it one left, and then we add the content of the tape, and the content of the tape is s prime, so the value of this function. So it is correct. And if the head moves left, then we want to be here. So we want to have this string without this last a0. So we have to just divide this number by 2. So this is of course this binary division is the result is always how to say it. So, for example, if the last bit of the number is 1, then it's just deleting the last bit. Okay, this operation. Maybe it is the easier way to say it. Oh, okay, and similar thing for B. We have two cases, whether the head moves to the left or to the right. So this is the same, but the other way around. So if the head moves to the right, we want to delete this B0. So we divide B by 2. And if the head moves to the left, we want to append the symbol written in this cell, so S prime to B. So we have to multiply B by 2 and add this new value, so G of Q and S. Okay, if the head moves to the left. Okay, now S. So again, if the head moves to the right, then the symbol observed by the cell will be B0. And if the head moves to the left, then the symbol observed by the head will be A0. So we have to have some way to extract this last bit from this number. But this is easy. So B0 first. So dividing by 2 deletes this bit, and multiplying by 2 this part will append 0. So if we subtract 2 times B divided by 2, then we will obtain from B, then we will obtain this bit. So maybe I will write it. B of t minus 2 times B t over 2. Yeah, so here we delete the last bit, B0. Then we append 0. So if we subtract from bt this number, we will obtain B0. So this is B0 if the head moves to the right. And the same thing for A. So it is A of t minus 2 times A of t over 2. Okay, if the head moves to the left. And the last one is easy. The next state is we only have to look at our function p, because the next state will be q prime, so p of q of t s of t. So here I wrote it as with pluses and times and dividing and so on, but we have shown on the previous lecture and tutorials that these are recursive functions, primitive recursive functions, so of course partial recursive functions. So, but I think that it is better to write it with dot or plus here than with this add or mult and compositions, because it wouldn't be easy to read. Okay, so we know that we can define these functions, and using only some basic operations. For now, all these operations are the ones that we know that are primitive recursive operations. And okay, so now if we define these functions, then what is the result of when m halts, then f of m of the input equals the concatenation of the following three strings: a of t me. I don't know if to write. Maybe I will write these dots here. Maybe I will write it in both versions, with dots and without dots. So this is a concatenation. In the moment that m halts, so this is the moment that halts. So where t me is, we can define this moment using unbounded minimum. So when our m Turing machine m halts, when it reaches the accepting state, so the accepting state is 0, so when q of t equals 0. Okay, so maybe I will write in bracket that t is the moment when m stops. So of course, if such moment exists, so if m halts, then such moment exists, and then this is the content of the tape, so the value of this function. And if m runs forever, then there is no such moment, so fm is undefined. So this is what we wanted. Okay, so this is the sketch of the proof, and we will use the similar construction of this dividing the tape into three parts and this multiplying and division by 2 on the previous lecture, on the next lecture, sorry, when we will discussing another topic. So yeah, so this is what I wanted to show you today. So this is the correspondence between functions and Turing machines. So we know, oh, so I forgot to tell you something. So maybe I will write it here now. So what we know now is that we have these three types of functions: primitive recursive functions, recursive functions, and partial recursive functions. And we have the following inequalities, maybe inclusions, I would say. The set of primitive recursive functions is a subset of the set of recursive functions and this is a subset of the set of the set of primitive recursive functions is a subset of the set of recursive functions, and this is a subset of the set of partial recursive functions. And of course, since these functions have to be total and this can be partial, and since we know that this corresponds to Turing machines with top property and this to general, we have inequality here, and here we also have inequality because we know that Ackermann function A belongs to this set. A belongs to the Ackermann function. That A does not belong to this set. It's not a primitive recursive function, but of course A is a recursive function because we can compute it on Turing machine and we will show it on the tutorials. Okay, so this is it for today, for the lecture. So now can we do the tutorials?
Sure.
Okay, so I think that I remember that there were some functions, some primitive recursive functions to define to check that they are primitive recursive functions. Yeah. Okay, so maybe let's move to the tutorials. I don't remember which one we have done. I will have to check it. Tutorial is a good one. Okay, so let's move. Where is 6 and 7? 6, 5, 4. I don't see 6 and 7. Why?
Because we've only just said that we are willing to do them.
Yeah, it should be at the bottom.
Oh, yeah. I see. Okay, so 6. Okay, so we have one volunteer, Mr. Janusz. So please 6.
Okay, give me a second.
Okay.
Okay. Well, my solution is very straightforward. I hope it's will be all right. Okay.
These are the best solutions.
Okay, it makes sense. So as we have only natural numbers, then signum of 0 will be always 0, and for any x, the successor is positive. So it is constant 1 in this case. So we have two constant functions.
But you are using, so which operation you are using to define it?
What do you mean?
Because we have this signum function is a function of one argument, yeah?
Yes.
It is not a zero function, it is not a projection function, and it is not a successor function. So we have to define it either as a composition or using the primitive recursion, yeah?
Yes,
So,
but I remember you said it the last time that the constant function also can be used.
Yeah, can be used, but in this scheme of primitive recursion, this h function is a function of one more variable than the defined function. So here fg has one variable, so h has to be a function of two variables. Yeah?
Yes, so it is.
It may be constant function, but it has to be defined as a function of two variables. So then you can use zero.
Yes, so generally I meant that h is a function of x and signum of x.
So you okay? So you use some projection or something like this, yeah?
Yes.
Okay,
I
so you have
don't use them, but this is the function of. Well, like I thought that if we can have g, that is. Okay, because g doesn't take any arguments.
Yeah, g. Yeah, so g is a constant zero, and h is a function of two variables.
And do we always need to use all of the variables?
We don't have to use variables. We can use projection and get rid of some variables.
Well, then, because I simply don't see the need of using any variables.
This is just a formal.
Okay. Okay.
Formal need. Yeah. So in this age, we have to get rid of one argument. Then we have only one argument. Then we can, for example, use zero function. Yeah. To this argument.
Okay. So we can have projection like p21 and have the composition with zero function. Yes.
Yeah.
And do the successor of it.
Yeah. Okay.
Okay. So I can reply
Okay.
and write it. H.
So maybe you can show us also the SG dash function or bar. I don't know how to.
That's what you meant by bar.
It is how it is written in LaTeX. I don't know how to
Well, I don't have
say.
it. Sorry, but I
Okay.
think it will be very similar. But just instead of cons 0, it will be just cons 1, which is a zero, a successor of 0 function.
But here we need a constant. Yeah, so this is just 1.
Okay. So then constant 1, and then h is a projection p to 1, for example, and it combined with 0 function. Yeah.
Okay.
Yes.
This is correct. So please write it and paste it here, and maybe
Okay.
So in the meantime, maybe we will do the next one. So number 7 is what was it? It was distance. Yes. So we have one volunteer, Miss Justyna. Can you do it?
Yes.
Okay.
So the bounded or limited difference, for it, the g will be defined with projection, and h will be defined with predecessor function that we've already proved, and again projection.
Okay. So LD of x0, it is x. Okay. So this is projection. Okay, correct. And LD of x1 plus 1. This is LD of LD. Okay, correct. So this is PT of okay, projection of we want the last variable. Okay, great.
Thank you.
So thumb and then plus. Okay, let's see this. 6. Okay, the next one is 8, and we have one volunteer, and we have already the solution. What is this ID? Ah, so okay, so this is this ID function, the function from the 7th point. So it was LD. So can you please it's to write change this I to I into L. Okay, so please paste it again. You can remove this post and post again. Okay.
Okay, I sent the new h for the signum function and the signum bar function.
Okay. Okay. Okay, and of course this G for the it is written here. It is constant 0. Okay. Okay. Correct. Okay. Now we are waiting for the 8th one to correct the correction of the 8th one. So we can go to 9, and we have one volunteer, Mr. Janusz.
Okay, so let me start with the less function.
And of course, we can use all the functions from the previous points.
Yes, sure. Okay. Okay, so this is my idea for the less function. Is it here? Yeah, it should be here.
Okay, so we have a corrected version of the 8. So this is what's going on. No. I have some problem with Teams. Okay, correct. So a down and a plus for the 8th point is okay. Okay, thank you. Correct. And now 9. So this is less than. Okay, let's see. Okay.
Well, maybe it is not the best notation with logical operators, but I just put them in these huge parentheses to differentiate between the logical values and the numerical ones.
Okay. And my idea is that because we have seen already some of these proofs of these definitions using this G and H, so okay. So this is ls of x0. We want it to be 0, so we define it as a constant 0.
Yeah, because for no x is less than 0. No natural x is greater than 0.
Correct, but this ls is a function of 2 variables. Yes, so we need
So then again I can do the
G has the function of 1 variable.
So then I can have that G is 0 function of projection to 1?
Yeah, correct.
Okay.
And the other one is if x is smaller than y plus 1. This BD is bounded difference.
Yeah, bounded difference.
Okay. So this is a composition of signal, bounded difference, and success.
Yes, signum is used only to binarize the result of bounded difference function.
Okay. Okay, this is correct.
Okay.
So we just need to correct this G.
Yes, I already replied below the photo.
Okay. Okay. So this was LS, and now the 2 remaining ones.
Okay. So give me a sec. Okay.
Okay, so maybe I will just make a comment that so maybe these points after the 12th one, so for 13 and so on, we will not use these formal definitions using this G and H, but just use the previous function. So if we, for example, have a composition, then we can just write this function as a composition, not using this formal H, G1, G2, and so on, or G and H in the case of primitive recursion. Yeah, so we just write it as a composition. So in a way that this LS could be written simply as, maybe I will, okay. So this LS, before I read GR. So we could define LS of X, Y as SG of LD in difference of Y Z, which is what is here in the end of H. Yeah, so I mean that for the points 13 to the end, we could define this function in this way. Yeah, like this is, we already know that SG and LD are primitive recursive functions. So, and of course, projections are primitive recursive functions, so we can swap the variables, and we see that LS is also primitive recursive functions. So now up to 12 we will use these formal definitions using H and G, and later, because they will be more complicated, we can use it in this way. Okay. Okay, and now I'm reading greater than. This is 1. Because every and what if X and Y are both 0?
Let me think. Then Y is 1. Then bounded difference is well, then bounded difference results in 0. Because
Yeah,
then we have. Ah, you mean like, okay, now I see. Like X is equal to 0 and yeah,
Y
sorry.
Yeah, so the H function is correct.
Okay. Yeah, now I see it. Sorry. Okay. So then maybe we can have here.
Yeah. So we need the function. This G is we need the function such that this function of G of X is equal to 1 if X is greater than 0, and G of X is equal to 0 if X is equal to 0. So I think we have already defined this function.
Yeah, we can have just signum of X.
Yeah.
Okay, so I will write below G should be signum of X, which is signum of X, then H is G is composed of okay.
Okay.
So
Maybe-
it's a composition of signum and projection.
Okay, so maybe not now, but later, could you please replace the solutions with the correct ones? So that other-
Okay.
Okay,
Okay, I can upload new photos.
okay, and okay, and what about the last one, equality?
Okay, let me send it.
So it is one if the arguments are the same and 0 otherwise.
That's a lot of photos. Give me a second. Okay.
Okay.
Okay, here it is.
Yeah, so this is signum of x, okay, projection and signum, and equality and y plus 1. H. So maybe I think that instead of using this less than and constant one, we could just write, we could again use signum or the complement of signum, yeah? It would be easier.
Yes, before I didn't know that we have the complement of signum, so that's why I use less than. But yes, in place of this less than and constant one, we could have the dashed signum.
Okay, so this is a term and the plus, but please replace these three photos with these better ones, okay?
Okay.
Okay, thank you. Okay, so this was I think 9, and 10 was done on the lecture. So now I think 11. Let me see. Okay, so now we don't have any volunteers. So so I suggest that for this part for this points 14, 15 up to 18, we can use less formal definitions without using this G and H. Just write them as a composition of the functions that we already know that are primitive recursive functions, like the one I wrote for LS. Less than. Yeah, so LS was just composition of signum and limited difference of swapped arguments. Okay, so we have somebody for 11, I think, but fast. 11. Okay, we have one volunteer for 11. So please, Mr. Janusz.
Okay. Okay, this is my idea.
Okay, so if y equals 0, then this is a product of only one number, so this is just p. Okay. So this is the composition of p and projections. Okay. And then we have, okay, the product of the first y plus 1 numbers times the last one, and this is the this is the composition of multiplication and projections. P and P of, okay. This is correct. Very well, plus and tam. Maybe tam and plus.
Okay, thank you.
Okay, so let's see on P. So this is the remainder, and I think it is very easy once we have the previous point, so the division. Yeah, so now we don't have to use this g and h anymore because these functions will be more complicated and they won't be easy to understand if we define them in this more formal way. So reminder, we want to divide y by x, and we already know the result. This was the quo function, and now we want to obtain the remainder. So now we don't have to use this g and h, and we just use the functions from the previous points. Maybe I should show one, so that you know how to go. Okay, anyone who wants to present the reminder, or shall I do it and you know how to, so you know how to present the next solutions? So basically, we want to use this y equals q times, how to write times without the star, x plus r. Yeah, this is it. Y, sorry, it should be plus, but I can edit it. Okay, so if we want to divide y by x, we get the following result: q and r. Q, we already have q. We have defined it in the previous point. This was the quo function, and now we want to get r. Yeah, so of course r equals y minus q times x. So sorry, again, edit q times x. So we know that y is not smaller than q times x, so it is bound difference or limited difference. Multiplication is also a primitive recursive function, so we can define it in this way. So my answer is the following. Remainder of x and y is the composition of limited difference of y and maybe I will add some spaces. Okay, of y and q times x, so q is 1 of x and y times x. Of course, this times is the same as this function multiplication defined in the second point. Okay, so this is the case where x is not 0, and maybe just in case we add signum of x. So if x is 0, then the whole product is 0, so the remainder is 0. Okay, this is my answer, and now we can present the answer like this. Yes, so without this gh, we know that multiplication, quotient, and limited difference are partially are primitive recursive functions, and swapping the arguments also, because these are projections. Okay, so do you see the solution of remainder?
Yes.
Yes. Okay. So you can present 15, 16, 17, 18 in this way. Okay, so now my question is, do you need some more time, or shall I give some hints, or I don't know? The next one is the question. Give x and y. The question is if y is divisible by x. Okay, I will upload another task. Okay, I have uploaded another task. So let's get back to this 15. So the question is y divisible by x? In the case that when both of them are positive, if one of them, if at least one of them is 0, then the result is 0. So when y is divisible by x, of course, when the remainder of division y by x is equal to 0. Yeah. So this is how we can define this function. Okay, do you need any more hints for the next one, for 15? Are you with me?
Could you give us a second?
Okay.
I think I can do it.
Okay, so please present the solution. Okay,
Give me a second to write it.
okay.
Okay, this is my idea.
Yeah, so this is in case where x and y are not zero, yeah? Because the definition of this function is that this is 1 if x is not 0, y is not 0, and y is divisible by x. So we have to add here that x and y are not 0, and we can do it in the same way as with this reminder, yeah? So in other words, if x is equal to 0 or if y is equal to 0, then the result should be 0. So we just have to multiply this by signum.
Okay, x and of signum of y. Yes.
Yeah, yeah. So if at least one of them is 0, then the total result will be also 0. And if none of them is 0, then the result will be this bar signum of Riemann.
Okay, is it like this?
This is very well, and this is a thumb and a plus.
Okay, thank you.
Okay. The next one is, I think we have 10 more minutes. The next one is the number of divisors. So it is 0 if the argument is 0, and the number of divisors otherwise.
Maybe could you write down this definition of the function, because it's hard to jump between documents.
Maybe I will write for the next one also. Number of divisors. Y for y greater. Okay. This is ND. Next one. PR. PR. Y P. Okay, these are the definitions.
Excuse me, someone who doesn't have the microphone just answered.
Yeah, I see it, and I'm writing the answer. Okay. So it is it's almost correct. One thing needs to be corrected. here we have div or of y and I is the question if I is divisible by y, and I think we need another way around. We want to check if y is divisible by I, yeah? Yes, so Miss Salah Asel, you need to correct only one thing. I don't know, sometimes these teams write the names of the users in the way that the first one is the name and the second one is the surname, and so sometimes the other way. And I don't know which is, sometimes I don't know which the name is and which is the surname. Yeah, this is correct. For Miss Asel, correct. This is a term. And a plus. So I will write the final answer, div y is sum from I equals 0 to y of div I y. Correct, a plus. Okay, so I have posted one more question, one more list, but with only one task. I have some more tasks for the next lecture, but I don't know if I think I shouldn't upload it yet because you don't know the definitions, and so on the next lecture we will discuss random access machines, and the exercises will be to write some programs, but we don't know the definitions and the instructions yet. So maybe we'll finish these two tasks on the next tutorials, and we will do this only one task from the next list, and I will discuss the random access machines exercises with you and leave them as a homework, I think. Okay, so we have two more left for the next week, okay?
Okay.
So thank you for your attention. See you next week. Of course, I will take photos of today's lecture and send them to the files section. Okay, so see you next week. Goodbye.
Thank you. Goodbye.
Thank you.
Goodbye.
Bye.